Welcome back to VTU Bros Hub. In this video, we're covering the most repeated and expected questions from graph theory. Module 2, explained in a way that's simple and super effective. Let's target 80+ marks and finish Module 2 strongly. Let's start with the first question in Module 2. It comes under Euler and Hamiltonian concepts, most repeated in VTU. Question. Define the following with example. An Euler graph. A connected graph is called an Euler graph if it contains an Euler circuit, which is a closed path that uses every edge exactly once. Condition. All vertices must have even degree. Example. Refer to the example graph shown. Zwei Euler path. An Euler path, or Euler trail, is a path in a graph that visits every edge exactly once, but does not return to the starting vertex. Condition. Exactly two vertices have odd degree and the graph is connected. Example. See the example given in the notes. Drei Euler circuit. An Euler circuit is a closed path that starts and ends at the same vertex and includes every edge exactly once. Condition. All vertices must have even degree and the graph must be connected. Example. Refer to the diagram provided. 4. Hamiltonian graph. A Hamiltonian graph is a graph that contains at least one Hamiltonian cycle, a cycle that visits every vertex exactly once and returns to the starting vertex. Example. Check the example graph shown. 5. Hamiltonian cycle. A Hamiltonian cycle, or circuit, is a cycle in a graph that visits every vertex exactly once and returns to the starting vertex. Example. Refer to the diagram in the material. 6. Hamiltonian path. A Hamiltonian path is a path that visits every vertex exactly once, but does not return to the starting vertex. Example. See the Hamiltonian path example. 7. Unicursal graph. A unicursal graph is a graph that contains an Eulerian trail. That is, a trail that uses every edge exactly once, but not necessarily a cycle. Example. Diagram given in notes shows this clearly. This one's all about Euler circuits and how to find them. Question. Define Euler circuit. Find the Euler circuit in the graph below. 1. Definition of Euler circuit. An Euler circuit in a connected graph is a closed trail that starts and ends at the same vertex, traverses every edge exactly once, may revisit vertices but never repeats an edge, and exists only if every vertex in the graph has even degree. 2. Verification of Eulerian condition. Let's now check if the graph is Eulerian. We list the degree of each vertex. Degree of vertex 1 is 2. Degree of vertex 2 is 6. Degree of vertex 3 is 2. Degree of vertex 4 is 4. Degree of vertex 5 is 2. Degree of vertex 6 is 4. Degree of vertex 7 is 4. Degree of vertex 8 is 2. Degree of vertex 9 is 4. Degree of vertex 10 is 4. Degree of vertex 11 is 4. Since all vertices have even degree, the graph is Eulerian. That means an Euler circuit exists. 3. Euler circuit. Here's one valid Euler circuit, starting and ending at vertex 1. Vertex 1 to vertex 9. Vertex 9 to vertex 8. Vertex 8 to vertex 7. Vertex 7 to vertex 10. And finally, vertex 2 to vertex 1. This path starts at vertex 1, ends at vertex 1, and uses every edge exactly once, without repetition. So this is a valid Euler circuit for the given graph. Let's now look at different types of graphs, based on whether they have a Hamiltonian path, Hamiltonian cycle, or Euler circuit. These are very commonly asked in VTU exams by giving specifying conditions. Let's go one by one. 1. Hamiltonian path but no Hamiltonian circuit. This graph has a Hamiltonian path but not a Hamiltonian circuit. Hamiltonian path A, B, C, D. Not a Hamiltonian circuit, because we don't return to the starting vertex. Refer to the example diagram. 2. Hamiltonian path and Hamiltonian circuit. Here, the graph has both a Hamiltonian path and a Hamiltonian circuit. Hamiltonian path, A, B, C, D, E. Hamiltonian circuit, A, B, C, D, E, A. Diagram clearly shows the cycle and path. 3. Neither Hamiltonian path nor Hamiltonian circuit. In this case, the graph has neither a Hamiltonian path nor a Hamiltonian circuit. No valid path that visits all vertices without repetition. Check the structure in the diagram. 4. Both Euler circuit and Hamiltonian cycle. This is a special case where the graph satisfies both conditions. Hamiltonian cycle 0, 1, 2, 3, 0. Euler circuit 0, 1, 2, 3, 0. Because every edge is visited once and all vertices have even degree. 5. Euler circuit but no Hamiltonian cycle. Graph edges AB, BD, DC, CA. Euler circuit A, B, D, C, A. No Hamiltonian cycle, because we can't visit all vertices once in a cycle. 6. Hamiltonian cycle but no Euler circuit. Graph edges AB, BC, CD, DA, BD. Hamiltonian cycle A, B, C, D, A. No Euler circuit, because vertex B and D have odd degrees. 7. Neither Hamiltonian cycle nor Euler circuit. Graph edges AB, AC, AD. No Euler circuit, because B, C, and D all have degree 1, odd degrees. No Hamiltonian cycle. Can't return to the starting vertex without repeating A. That's it for the different graph types. Make sure to practice drawing these diagrams. Let's go to the next repeated theory question from Euler graph. Question: prove that a connected graph G is an Euler graph if and only if all vertices of G are of even degree. Statement: a connected graph G is an Euler graph if and only if all vertices of G are of even degree. Proof: in a connected graph G, if all the vertices are of even degree, then we can construct an Euler circuit by choosing any vertex as the starting point and traversing all edges exactly once, without getting stuck at any vertex. This is possible because at every step, there is an even number of untraversed edges at each vertex. Hence, G is an Euler graph. Let's move to the next expected question. This one is from Hamiltonian circuits and complete graphs. Question: in a complete graph with n vertices, prove that there are n-1 divided by 2 edge-disjoint Hamiltonian circuits. If n is an odd number and greater than or equal to 3, first, what's a complete graph? A complete graph, called Kn, is a graph where every vertex is connected to every other vertex. In Kn, the total number of edges is maximum. And since it's fully connected, you can form Hamiltonian circuits easily. A Hamiltonian circuit is a cycle that visits every vertex once and returns to the starting vertex. Now the important part. Edge-disjoint means that all the Hamiltonian circuits should use different edges. No edge should repeat across circuits. Now the key result? If n is an odd number greater than or equal to 3, then the number of edge-disjoint Hamiltonian circuits is n-1 divided by 2. This result is proved using the rotation technique, by rotating vertex positions to create new unique circuits. For example, if n equals 5, then -1 divided by 2 equals 2 circuits. In K5, you can draw exactly 2 edge-disjoint Hamiltonian circuits. Refer to the diagram in your notes to see the construction. The final answer. In a complete graph with n vertices, where n is odd and greater than or equal to 3, the number of edge-disjoint Hamiltonian circuits is n-1 divided by 2. That's a clean scoring theory. Just remember the condition and formula. Let's take a direct application question from Hamiltonian circuits. Question: how many edge-disjoint Hamiltonian cycles exist in a complete graph with 5 or 7 vertices? Draw the graph to show and specify the cycles. A Hamiltonian cycle is a cycle that visits every vertex exactly once and returns to the starting vertex. In a complete graph, the maximum number of edge-disjoint Hamiltonian cycles is given by n-1 divided by 2. So for n equals 5, 5 minus 1 divided by 2 equals 2 edge-disjoint Hamiltonian cycles. Let's say the 5 vertices are A, B, C, D, and E. Here are the 2 edge-disjoint Hamiltonian cycles. Cycle 1. A to B to C to D to E to A. Edges used AB, BC, CD, DE, EA. Cycle 2. A to C to E to B to D to A. Edges used AC, CE, EB, BD, DA. As you can see, the 2 cycles do not share any edge, so they are completely edge-disjoint. Total number of edges in the complete graph with 5 vertices is 5 times 4 divided by 2 equals 10 edges. Each Hamiltonian cycle uses 5 edges, so 2 edge-disjoint cycles use all 10 edges without overlap. Final answer: There are two edge-disjoint Hamiltonian cycles in the complete graph with 5 vertices. They are A to B to C to D to E to A and A to C to E to B to D to A. Now let's look at a popular application in graph theory, the traveling salesman problem, or TSP. Question: illustrate the traveling salesman problem using a graph. In this problem, a salesman is located in a starting city. He must visit every other city exactly once and return back to where he started, while traveling the least total distance. This is shown using a weighted graph. Vertices represent cities. Edges represent routes. Weights on the edges represent the distance or cost of travel. The goal is to find a Hamiltonian circuit with the lowest total weight. That means visit all vertices once, return to start, and keep the total cost as low as possible. You'll understand this better by seeing the example graph shown. It will show the cities, connections, and distances. Once the graph is given, we try different possible routes, calculate the total weight of each, and select the one with minimum total distance. So in short, the traveling salesman problem is about finding the shortest round-trip path that visits all cities once and comes back. That's how we illustrate TSP using a graph. Let's now solve a full traveling salesman problem step by step, using the given weighted graph. Question: solve TSP for a graph with 4 vertices and find the optimal Hamiltonian circuit with minimum total cost. First, the number of cities is 4, so number of possible routes equals n-1 factorial, which is 4 minus 1 factorial, or 3 factorial, giving 6 possible paths. We'll fix the starting vertex as A and write all 6 paths that start and end at A. Let's now list all 6 paths and calculate the total cost for each one. A 2B to C to D to A equals 2 plus 8 plus 1 plus 7, total 18. A to B to D to C to A equals 5 plus 8 plus 3 plus 7, total 23. A to C to B to D to A equals 7 plus 3 plus 8 plus 5, total 23. A to D to B to C to A equals 2 plus 3 plus 1 plus 5, total 11. A to B to D to C to A equals 5 plus 1 plus 3 plus 2, total 11. A to C to D to B to A equals 7 plus 1 plus 8 plus 2, total 18. Now from the 6 total paths, the 2 shortest paths have cost equal to 11. So the optimal solutions are A to D to B to C to A and A to B to D to C to A. These are the Hamiltonian circuits with minimum total weight. You can draw either of these two as the final answer. Final answer: the optimal Hamiltonian circuit has cost 11, and the best routes are A to B to D to C to A, or A to D to B to C to A. That is the answer. Write it as shown above. Let's solve the traveling salesman problem, one of the most practical applications in graph theory. Question: a salesman starts from city A and wants to visit every other city exactly once, then return back to A while traveling the minimum total distance. This is a TSP, and we solve it using Hamiltonian circuits in a weighted graph. Vertices represent cities. Edge weights represent distances between cities. Step 1. Count how many cities are in the graph. Let's say n. Then the number of possible routes equals n-1 factorial, because we fixed the starting point as city A and arrange the rest in all possible orders. Step 2. List all possible Hamiltonian circuits that start and end at A and visit all other cities once. Write down the total distance for each route by adding the edge weights. Step 3. Compare the total distances of all routes. The one with the lowest total weight is the optimal solution. You'll understand better by looking at the example graph shown and checking each path and its cost. Final answer: the salesman should choose the shortest route among all possible circuits, and the total distance will be the minimum sum of edge weights. That's how we solve the traveling salesman problem, step by step using a weighted graph. Let's now go through another important VTU concept: directed graphs, also known as digraphs. Question: define directed graph. Find the in-degree and out-degree of the following graph. Definition: a directed graph, or digraph, is a graph in which each edge has a direction. It is written as an ordered pair, open bracket U, V, close bracket, which means there is a directed edge from vertex U to vertex V. Vertices are the points or nodes. Directed edges, also called arcs, are arrows from one vertex to another. If the edge from U to V exists, the edge from V to U may or may not exist. So a digraph is not symmetric. Observe the example graph shown. It contains 5 vertices and 10 directed edges. Each arrow shows the direction of the edge, in degree and out degree. Let's now find the in degree and out degree of each vertex. In degree is the number of arrows coming into a vertex. Out degree is the number of arrows going out from a vertex. Observe the graph and count the incoming and outgoing arrows for each vertex. Fill the values in the table shown beside the graph. This completes your answer. Let's now go through the most expected theory list. Types of directed graphs, also called digraphs. Question. Explain different types of digraphs with suitable examples. 1. Simple digraph. A simple digraph is a directed graph with no loops and no multiple directed edges between the same pair of vertices. Observe the example diagram shown. 2. Symmetric digraph. A digraph is symmetric if for every edge from U to V. The reverse edge from V to U also exists. Check the example graph for clear symmetry. 3. Asymmetric digraph. A digraph is asymmetric if no two vertices are connected in both directions. If there is an edge from U to V, then V to U does not exist. Also, no loops are allowed. Observe the example graph shown. 4. Simple symmetric digraph. A simple symmetric digraph has no loops or multiple edges, and also satisfies the symmetric property. Refer to the diagram given. 5. Simple asymmetric digraph. This is a simple digraph with no reverse edges. So it's asymmetric and has no loops or multiple edges. Observe the example shown below. 6. Complete digraph. In a complete digraph, every pair of distinct vertices has at least one directed edge, either from U to V or V to U or both. Check the full connection in the example graph. 7. Complete symmetric digraph. This type has both directions between every pair of vertices. So for every U to V, there is also V to U. Observe the symmetric connection in the diagram. 8. Complete asymmetric digraph. Here, each pair of distinct vertices has only one directed edge, not both. This is also known as a tournament graph. Refer to the tournament example graph shown. 9. Balanced digraph. A digraph is called balanced if for every vertex, the in degree equals the out degree. You can see this clearly in the example given. That completes all types of directed graphs with examples. It's a full 7-mark theory question. Revise and draw every type once. Let's now take a simple but important proof in digraphs. Question. Prove that in any directed graph, the sum of in degrees of all vertices is equal to the sum of out degrees, and both are equal to the total number of edges. Statement. In any directed graph, the sum of all in degrees equals the sum of all out degrees, and both are equal to the number of edges. Proof. Each directed edge goes from one vertex to another, so it contributes one to the out degree of the starting vertex, and one to the in degree of the ending vertex. That means every edge adds one in degree and one out degree. Let's say the total number of edges in the digraph is E. Then the sum of all in degrees is E, and the sum of all out degrees is also E. This can be written as sum of in degrees equals sum of out degrees equals number of edges. So we conclude, the summation of in degree of all vertices equals the summation of out degree of all vertices, which is equal to the total number of edges, hence proved. Let's now go through the important theory. Types of binary relations, using examples and digraphs. Question. Explain different types of binary relations. 1. Reflexive relation. A relation R on set A is reflexive if for every element A in A, the pair A is in R. Reflexive digraph. Has a self-loop at every vertex. Example. A equals set of 1, 2, 3. R equals 1, 1, 2, 2, 3, 3. Irreflexive digraph. Has no self-loops at any vertex. Example. R equals 1, 2, 2, 3. No pair like AA is present. 2. Symmetric relation. A relation is symmetric if whenever a comma B is in R, then B comma A is also in R. Symmetric digraph. Every arrow has a reverse arrow. Example. If 1, 2 is in R, then 2, 1 must also be in R. 3. Transitive relation. A relation is transitive if whenever a comma B and B comma C are in R, then a comma C is also in R. Example. R equals 1, 2, 2, 3, 1, 3 is transitive. 4. Equivalence relation. A relation is called an equivalence relation if it satisfies all three properties: reflexive, symmetric, and transitive. Example. A equals set of 1, 2. R equals 1, 1. For 1, 2, 1, 2. 1. Reflexive, 1, 1. and 2.2. Symmetric, 1, 2, and 2.1. Transitive, 1, 2, and 2.1 imply 1.1, and so on. That completes the types of binary relations. Let's represent the relation R on set A equals 2, 3, 4, 6, where R is defined by the phrase is a factor of. We draw a directed edge from A to B if AA is a factor of B. Example, 2 is a factor of 4 and 6, so we draw arrows from 2 to 4 and from 2 to 6. Now repeat this for all valid pairs in the set. Check if one number divides another without remainder. Draw an arrow from it to B, only if A divides B exactly. The resulting digraph will show the relation clearly. That's how we represent the relation is a factor of using a directed graph. Let's now look at the most common operations on graphs, each explained clearly with an example. Question: list and explain different operations on graphs. 1. Union. G equals G1 union G2. It combines all vertices and all edges from both graphs. Refer to the union example graph shown. 2. Intersection. G equals G1 intersection G2. It includes only the common vertices and edges from both graphs. Observe the intersection graph example. 3. Ring sum or symmetric difference. G equals G1 ring sum G2. This keeps edges that appear in either one, but not both. See the symmetric difference example. 4. Complement of a graph. Called complement of G. Adds edges between non-connected vertices and removes the existing ones. Refer to the complement graph diagram. Sync, fusion, combines two vertices into one, and connects the result to all neighbors of the originals. Check the fusion example shown. 6. Decomposition. Splits a graph into subgraphs like paths, cycles, or trees. Observe the decomposition diagram. 7. Deletion. Includes vertex deletion. Removes a vertex and its edges. Edge deletion. Removes only the selected edge. Refer to the deletion examples for both. That completes all graph operations. Very important for scoring in theory questions. Thanks for watching, bro. If this helped you revise Module 2 clearly, make sure to like the video, share it with your friends, and follow VTU Bros Hub for more smart revision like this.